there's one more thing that I'd like to do today before we end our lecture. So we've seen how given a function like 3n cubed plus n squared, we can figure out the order of growth by applying our two simplifications. We lop off this low order term, lose this multiplicative constant, and we have n cubed. So what we're going to do in this little video is introduce some formal mathematical notation known as Big-Theta, which at first will seem maybe a little daunting and scary, but it's not so bad. It turns out there's nothing different about Big-Theta than what we've been doing so far. It's just a definition that mathematically, rigorously captures what we've been trying to do. So before I tell you what Big-Theta is, I want you to tell me what is the order of growth of these 5 functions. In other words, what's its shape? I'll give you a chance to think about this, and I'll tell you my answers. Okay, so my answers are n to the 4th, n cubed, 1, n times e to the n, and n squared. Before we get to Big-Theta, let me just talk about these last 3 here. So 1 over n, as n goes to infinity, that's going to diminish to nothing, and we're left with just a constant, and we'll typically write that constant as 1. N times e to the n plus n, well, this left term is much bigger, and neither of these two parts of this term are constants, so we keep them. And then for our final example, 4n squared, obviously for very large n, is going to be much larger than 40 sine n, which varies between minus 40 and 40. So this here, you might have felt a little shaky about these last 3 choices, and that's where Big-Theta is going to be useful. It's going to give us a really firm foundation to stand on. And so before I define Big-Theta, let me just tell you how we use the term. So ordinarily, before this part of the lecture, we would have said, for example, n cubed plus 3n to the 4th, it has order of growth n to the 4th. Now we're going to say it belongs to Big-Theta n to the 4th. Now sometimes people also use an equal symbol here. Either way is fine. But it basically just says, if you'd like, you could think of it as it is in the order n to the 4th. There's a family of functions that all grow like n to the 4th, and this is one of them. It belongs to the family, and that's nice. Now, how do you actually define Big-Theta rigorously? Well, some clever folks, not quite a century ago, said, okay, suppose we have a function r of n that belongs to the order f of n. Well, that means that there are 2 constants, k1 and k2, must be positive, such that k1 times f of n, which you can think of as a small version of f of n, is less than or equal to the function of interest, which is in turn less than or equal to a big version of f of n. And that has to be true only for really large n. So let's see an example to drive that home. Let's consider 40 sine n plus 4n squared. I said that belongs to the order n squared. So that's saying the function r of n, it's a function of interest. It belongs to the order n squared. And I'm going to pick 2 constants. In this case, k1 is 3 and k2 is 5. Now, those are not the only possible choices, but what's special about those choices is that we think about this function and we say, okay, for really large n, obviously, this is only the 4n squared is really going to matter, and that's going to be big greater than 3n squared and less than or equal to 5n squared. Let's see a picture. I think that should help. Okay. So this here, the red line shows r of n over as n gets bigger. And we can see that for very large n, it does actually look a lot like n squared. In fact, it fits between 3n squared, which is the bottom line, and 5n squared, which is the top line. Now, of course, for small n, I mean, it's wiggling in and out. But if we zoom out, we can see this is basically just a parabola. All right? I'll give you guys a chance to try one out. So what I'd like you to do is, let's suppose your function of interest is 4n squared plus 3 times n times the natural log of n, all divided by 2. So come up with a simple f of n, the family that r belongs to, and a corresponding k1 and k2. All right, my answer is it also belongs to the family n squared. For really large n, this part just doesn't matter. And since 4n squared divided by 2 is 2n squared, the k1 I picked was 1, and the k2 I picked was 3. So let's do a little visualization here. And we can see that, okay, for small n, this function, it dips below 0 actually, but then for very large n, well, it comfortably sits between n squared and 3n squared. Now these do not have to be integers. I mean, we can do 2.5, maybe that's Well, it's a harder choice to see. But you can pick, they can be non-integers as well, by the way. Okay, that's all. That's all there is to it. So it captures in a mathematically precise way our intuition about growing like a function by saying that you're bigger than a small version of that function, but smaller than a bigger version of that function. And that's it. Now, I'll note that using Big-Theta, it does not change anything at all about the way we do runtime analysis. We still collect counts of operations. We still think about the order of growth. The only difference is that anywhere we would have said order of growth, we'll now use Big-Theta. And so, for example, if we counted all of our operations, we could just collect the worst case count in Big-Theta notation and say, okay, the number of less thans is theta n squared and so forth. And then we could summarize this table by focusing only on a single operation. And we'd get, in this case, that the worst case runtime is Big-Theta n squared.